Good morning, students. Myself, Srishtie Chaudhary, working as lecturer in Electronics and Communication Engineering Department in Government Polytechnic College for Girls at Patiala. Today, I am here to discuss upon the topic of antennas. In antennas, this word we have mostly used in case of your communication system, whether it is a optical communication system or whether it is a wireless communication system or general communication system. This word antennas is used mostly. The antennas can be a transmitting antenna or it can be a receiving antenna. So now today we are going to discuss about the basic structure, why antennas are needed, what are the types of antennas. All these contents will be covered in this lecture. So this is the basic slide of the contents which will be covered in this lecture, as the history of the antennas, how the antennas emerged, when the antennas were started, the introduction of antennas, a basic definition and the intro of your antennas, the basic structure of antenna, how antennas are constructed and of what material the antennas are constructed, the need of antennas, why the antennas are needed by us, what is the basic requirement for an antenna in a communication system. Next, the types of antennas according to their application or according to their length, the types of antennas, and also we are going to discuss some of the antennas in detail. Next is the parameters involved, the parameters that are involved with respect to your antennas, as the beam width, radiation pattern, directive or power gain, and at last the applications of antennas where your antennas are used. So coming with the first history of the antenna, the first antennas were built in 1888 by German physicist Heinrich Hertz in his pioneering experiments to prove the existence of electromagnetic waves predicted by the theory of James Clerk Maxwell. What did Hertz did? The Hertz placed dipole antennas at the focal point of parabolic reflectors for both transmitting as well as for your receiving antenna. And this work of Hertz is also published further in Annalen der Physik und Chemie, volume 36, 1889. So he has proved his work by the publication. Now coming to the introduction of your antenna, what basically antenna is. An antenna is an electrical device which converts electric currents into radio waves and vice versa, that is again the radio waves are converted into the electric currents. This conversion depends your antenna is working as a transmitting antenna or it is working as a receiving antenna. If it is working as your transmitting antennas, then the conversion will be from electric currents into the radio waves, and if it is working as a receiving antenna, then the conversion will be from radio waves to your electric currents. It is usually used with the radio transmitter or radio receiver, as I have discussed. Now during the conversion, the medium used in between the transmitter and in between the receiver is the free space, that is you are using the atmosphere as a communication medium between the transmitter and between the receiver. In transmission, a radio transmitter applies an oscillating radio frequency electric current to the antenna's terminals, that is antenna terminals are provided with this oscillating radio frequency, and then the antenna radiates the energy from current as electromagnetic waves that are known as your radio waves, which travel in the free space. Now defining the antenna as a transmitting antenna or as a receiving antenna, both can be defined as, first the transmitting antenna can be defined as any structure that is designed to efficiently radiate electromagnetic radiation in preferred direction, that is the transmitting antenna. We know the transmitters have the basic requirement that it has to transmit the signal to a particular direction. So what is a transmitting antenna? It is also transmitting the signal or information in a particular direction. Here it is radiation mechanism that is used, that you are radiating the energy from one particular terminal to another particular terminal. In reception, an antenna intercepts some of the power of an electromagnetic wave in order to produce a tiny voltage at its terminal that is applied to a receiver to be amplified. Any antenna can be used for both transmitting and receiving, and similarly we can define the receiving antenna. again, it is any structure that is designed to efficiently receive electromagnetic radiation, that is electromagnetic waves, that is called your receiving antenna. Now, coming on the basic structure of your antenna, what is an antenna constitute of, what is the construction of your basic antenna. It is a metallic conductor system capable of radiating and receiving EM waves, that is, it radiates EM energy or it receives EM energy, again depending upon the criteria that it is working as in transmitter or working as in receiver. Typically, an antenna consists of an arrangement of metallic conductors that are known as your elements, electrically connected, that these elements are electrically connected, can be connected through a transmission line to a receiver or to a transmitter. Any oscillating current of electrons forced through the antenna by a transmitter will create an oscillating magnetic field around the antenna elements, while the charge of the electrons also creates an oscillating electric field along the elements. Now, when these fields are created, these are time varying fields. According to the time, the field will vary. These time varying fields radiate away from antenna into the space. We are using the free space as the communication medium. So these are time varying fields are radiating into the free space as moving electromagnetic field wave. Conversely, during reception, the oscillating electric and magnetic fields of an incoming radio wave exert force on electrons in the antenna elements, causing them to move back and forth, creating oscillating currents in the antenna. So when during the reception these fields are being received as an incoming signal, the radio waves are received. These radio waves will exert force on the electrons that are present in the antenna elements. These force will provide back and forth and create oscillations in your antennas. Antenna reciprocity, this is the basic principle of your antennas. If a antenna can be used as a transmitter and as well as a receiver, it provides this principle. For example, in a two-way communication, same antenna can be used as a transmitter and a receiver. The practical day-to-day or a real-time example for this antenna reciprocity is your mobile phones. The antenna attached to your mobile phones follow this antenna reciprocity. Your mobile phone's antenna work as a transmitting antenna as well as a receiving antenna. It transmits your signal from one particular destination to source to another destination, that is from one particular mobile to another particular subscriber or mobile, and again as being a receiver, it receives the signal from one source to its destination or from one subscriber to being a subscriber. Now, antenna may also contain reflective or directive elements or surfaces that are not connected to the transmitter or receiver, such as parasitic elements, parabolic reflectors or horns, which serve to direct the radio waves into a beam or other desired radiation pattern. That is, they just provide the direction for your radio waves. As the name indicates, these are the parasitic elements. Why they are named so parasitic elements? Parasitic elements are those elements, they don't have their own active source, they don't provide any active operation for your antennas, they just direct the radiation of your EM waves or the radio waves, so they are known as your parasitic elements. Antennas can be designed to transmit or receive radio waves in all directions equally, and if it transmit or receive in all directions equally, it is known as your omnidirectional antenna. And if it transmits them in a beam in a particular direction, intended in a one particular direction you want to transmit or receive, and in that particular direction, then it is known as a directional or high gain antennas, as it is not transmitting or receiving in all the directions, in only one particular direction it is transmitting or receiving, so it is known as your directional antenna. Now, why antennas are needed? What is the need of antenna in our daily routine life, or why we need antennas in our communication systems? It can be explained as follow, that if we need antenna, the basic requirement was if the two persons want to communicate with each other. Now, we know that two persons can communicate with each other easily, then why antennas needed? But if the two persons which want to communicate with each other are separated by some distance, and between that distance the wired communication is not possible. Practically the wired communication cannot be implemented between the two persons that want to communicate. That is, you are having a wireless communication, the requirement is a wireless communication. At that point antennas are needed so that one person can communicate to another person without any wired communication. Antennas are required by any radio receiver or transmitter to couple its electrical connection to electromagnetic field. Radio waves are electromagnetic waves which carry signals through the air. As we have discussed that air is the medium, or free space is the medium between the transmitter and the receiver, and these waves are at the speed of light with almost no transmission loss. Radio transmitters and receivers are used to convey signals in systems including broadcast, radio, television, mobile telephones, point to point, and satellite links. Radio waves are also used for measurements in technologies as radar. In each and every case, transmitter and receiver involved require the antennas. Although these antennas sometimes are hidden, such as antenna inside an AM radio or inside a laptop computer equipped with Wi-Fi. These antennas in this AM radio receiver or in Wi-Fi was not needed. Also, the need of antenna can be explained again with the same example of your mobile phones. You are using your mobile phones. By using that mobile phones, you are communicating with another person that is separated by you with some distance, and the wired communication is not there between you and that particular second subscriber that is using the mobile. You are using the wireless communication again. So here the need of antennas emerge. If you want, being a person, you are using a mobile phone, another person using a mobile phone, and you both are separated with the particular distance in between, and wired communication is not possible. You are using a wireless communication. So this is why the antennas are needed. You want to communicate, and this communication is provided by your antennas. And also the antennas is not possibly that all the times are visible. The antennas can be sometimes hidden, as we have given the example in the radio receivers or in the computers with Wi-Fi equipped. Now, where these are used, antennas, we have discussed basic structure, why we need the antennas. Now, where these are used, antennas? Antennas are used in systems such as radio and television broadcasting, point-to-point radio communication, wireless LAN, radar, and space. Antennas are most utilized in air or outer space, but can also be operated underwater or even through soil and rock at certain frequencies for short distances. Now, the radiation mechanism, this is the basic principle that is followed in case of your antennas. What is this radiation mechanism? This radiation mechanism can be understood by two-wire transmission line concept. In the diagram, we have shown the two-wire transmission line concept, where at the one side you are having the generator, at the one side of the transmission line you are having the source generator, and other end of the transmission line is left open circuited. Now, ideally all the incident energy must be reflected back when open circuited. This is the ideal concept of your two-wire transmission line. But during operation, practically a small portion of electromagnetic energy escapes from the system, and that is, it gets radiated. This escape of energy is known as your radiation. Now, why this occurs? This occurs because the line of force do not undergo complete phase reversal, and some of them escapes. So the amount of energy is very small due to the mismatch between the transmission line and the surrounding space. The second reason for this is also because the two wires are too close to each other. The two-wire transmission line concept we are discussing here, the two wires that we are assuming that are very close to each other, and the radiation from one tip will cancel radiation from the other tip, as there are opposite polarities and distance between them is too small as compared to the wavelength. So we need to increase this radiation. To increase this radiation, the transmission lines are enlarged. Here the diagram shows that at the end the transmission lines are opened up. You are enlarging the transmission lines at the open circuited end so that the amount of radiated power can be increased. So to increase the amount of radiated power, open circuit must be enlarged by spreading the two wires. Due to this arrangement, coupling between transmission line and free space is improved, almost amount of cancellation has reduced, and the radiation efficiency will increase further if two conductors of transmission line are bent so as to bring them in the same line. This can be explained as that if these conductor lines are enlarged so much that they are on the same line, you are having these on the same line, the radiation can be improved further. And this, when you have merged them in the same line, same plane, this gives the emergence of your dipole antenna. Here how your dipole antenna emerges. Now if the length of this transmission line in the same plane is lambda by 2, you are having the half wave dipole antenna, which will be discussed in the preceding lecture. Now types of antennas. We have discussed the antennas, the basic structure of antennas. The types of antennas, the antennas can be defined or differentiated according to their applications and technology, and also according to their length or the structure of your antennas. Now first, according to their application and technology available, antennas fall in two categories. One is omnidirectional and one is directional. Omnidirectional can also be said as your weakly directional antennas, which receive or radiate more or less in all directions. These are employed when the relative position of other station is unknown or arbitrary. They are also used at lower frequencies where a directional antenna would be too large, or simply to cut cost in applications where a directional antenna is not required. So in general, omnidirectional antenna radiates or receives in all directions. Second is the directional antenna, also known as your beam antenna, which are intended to radiate or receive in particular direction or a particular directional pattern. That is, they cannot radiate or receive in all the directions, only in particular direction they radiate more. These are your directional antennas. Now according to the length of transmission lines available, antennas generally fall in one of two categories. One is resonant and one is non-resonant antenna. The resonant antennas is a transmission line, the length of which is exactly equal to multiples of half wavelength, and it is open at both ends. Now equal to multiples of half wavelength, that is the multiples of lambda by 2, that is multiples can be labeled as m, that is m lambda by 2. So if your m is equal to 2, you are having resonant antenna as lambda. If you are having m is equal to 3, you are having 3 lambda by 2. If you are having m equal to 4, you are having 2 lambda, so on, that is you are having the multiples of half wavelength. In non-resonant antennas, the length of these antennas is not equal to exact multiples of half wavelength. In these antennas, standing waves are not present, as antennas are terminated in correct impedance, and the waves travel only in forward direction, and it is a unidirectional antenna. Now coming to the some basic parameters that are involved in case of your antennas. First is the radiation pattern. What do you mean by radiation pattern? Radiation pattern is the graphical representation of the energy escaped or energy radiated by an antenna, or simply field strength graph of your antenna. This in this slide, the radiation pattern is shown, and the radiation pattern is plotted on a coordinate copolar plot. Here it is seen the coordinate copolar plot, and here you are having the various radiation patterns, that is the energy radiated by the antenna. Now radiated energy in a particular direction with the maximum radiation forming a lobe is your main lobe. That is, at a particular direction where there is the maximum radiation, the lobe at that side is known as your main lobe, and other lobes are known as your side lobes. But the lobe that is exactly opposite of your main lobe, that is of maximum radiation lobe, it is known as your back lobe. This lobe is also known as your side lobe as well as your back lobe. Other lobes cannot be defined as your back lobes, these are only the side lobes or minor lobes. Only the lobe that is exact opposite of your main lobe is known as your back lobe, also known as your minor lobe. Now the radiation pattern of an antenna as I have discussed, is a plot of relative field strength of radio waves emitted by the antenna at different angles. It is typically represented by three-dimensional graph or polar plots of horizontal and vertical cross section, and it is a plot of field strength in volts per meter versus the angle in degrees. The pattern of an ideal isotropic antenna, which radiates equally in all directions, would look like a sphere. Many non-directional antennas, such as dipoles, emit equal power in all horizontal directions, with the power dropping off at higher and lower angles. And this is called as an omnidirectional pattern, and when plotted looks like a donut. Now the radiation of many antennas shows the pattern of maxima known as lobes, which we have seen in the diagram, at various angles separated by nulls. Nulls are the angles where the radiation falls to zero. You are not having any maximum points here. This is because radio waves emitted by different parts of the antenna typically interfere, causing maxima at angles where the radio waves arrive at distant point in phase. Maxima are points where radio waves from various parts are in phase, and nulls are points where zero radiation is there, that is radio waves arrive out of phase. We are having null points. In a directional antenna designed to project radio waves in particular direction, the lobe in that direction is designed larger than the other lobes. That is, to that particular direction you are having the main lobe with maximum radiation to that particular direction. The other lobes, as I have discussed, represent unwanted radiation and are called side lobes. The axis through the main lobe is called the principal axis. Now second is the antenna gain. It is the parameter which measures the degree of directivity of antenna's radiation pattern. High gain antenna will proficiently radiate in a particular direction. Antenna gain can further be defined as your directive gain or your power gain. The antenna gain is basically a ratio of the power from a directional antenna to an isotropic antenna. This ratio depends further taking into account the power, that the power is fed or power is radiated. If we are having the ratio of power fed to an directional antenna to the power fed by an isotropic antenna, then we are having the directive gain. And if we are having that the power radiated by a directional antenna to power radiated by the isotropic antenna, we are having the another gain. So both have the difference, that it is power radiated or it is power fed to the antenna. The ratio remains the same. The ratio taken is from the directional antenna to your isotropic antenna. So specifically, antenna gain or power gain of antenna is defined as the ratio of intensity radiated by the antenna. Power gain is the radiated by antenna in the direction of its maximum output at an arbitrary distance divided by the intensity radiated at the same distance by isotropic antenna. This is your power gain. The gain of an antenna is passive phenomenon. Power is not added by antenna, but it is simply redistributed. High gain antennas have advantage of longer range, and low gain have the shorter range. Now, for example, dish antenna spacecraft is a high gain device that must be pointed at the planet to be effective, whereas a typical Wi-Fi antenna in laptop computer is a low gain antenna, and as long as base station is within the range, antenna can be in any orientation in space. In your daily routine, you use laptops equipped with Wi-Fi. You are not concerned with the orientation of your laptop because it is your short range antenna. You can place it anywhere until unless you are within the range. In practice, the half wave dipole is taken as reference instead of isotropic radiator. The gain is then given in decibels over dipole. Now, antenna efficiency of a transmitting antenna is the ratio of power actually radiated to power absorbed by the antenna terminals. The power supplied to the antenna terminals, which is not radiated, is converted into heat. This usually through loss resistance in antennas conductors, but can also be due to the dielectric or magnetic core losses in antennas. Now, next parameter is your polarization. The polarization of an antenna is the orientation of electric field of radio waves. This can also be simplified as the polarization is the direction at which your electric field is there. So, polarization of antenna is the orientation of electric field of radio waves with respect to the earth's surface, and is determined by the physical structure of antenna and by its orientation. That physical structure means how your antenna is constructed, and orientation means that at which particular direction your antenna is placed. A simple straight wire antenna will have one polarization when mounted vertically and a different polarization when mounted horizontally. That is, when you change the direction of the placement of your antenna, your polarization changes. Reflections generally affect the polarization. For radio waves, most important reflector is the ionosphere signal, and the signals which reflect from it will have their polarization changed. Low frequency, very low frequency and medium frequency antennas are vertically polarized. Next parameter is the beam width. Beam width of an antenna is defined as angular separation between two half power points on power density radiation pattern, or it can also be defined as angular separation between 2-3 dB down points on the field strength of radiation pattern, and it is expressed in degrees. This can be explained in clearly by this example here. The difference between these two half power points is known as your beam width. Also, according to your second definition, it is the here the difference between this point and this point is 3 dB. So 3 dB down, and the difference between two points is your beam width. As the diagram, angular separation between 2-3 dB down points. Here you are 3 dB down, and angular separation between these 2-3 dB down points is known as your beam width. Now coming to the antennas, first antenna is your isotropic antenna, which is a hypothetical antenna. That is, in practical this antenna does not exist. It is just a concept or used for the reference to describe real antennas. Isotropic antennas radiates equally in all directions. Its radiation pattern is represented by a sphere as shown here, that it radiates equally in all directions, whose center coincides with the location of isotropic radiator. It is considered to be a point in space with no dimensions and no mass. This antenna cannot exist physically, but it is useful as a theoretical model for comparison with all other antennas. Most antenna gains are measured with reference to an isotropic radiator and are radiated in decibels with respect to an isotropic radiator. Now, why it is physically not possible? Because during the operation, practically we cannot have an antenna that radiates in all the directions equally. So practically this antenna is not possible. Now, half wave dipole antenna, we started the radiation mechanism, and due to radiation mechanism we came into the end with the emergence of your dipole antenna. And I said that when the length of your dipole antenna is lambda by 2, you are having a half wave dipole antenna. So the half wave dipole antenna is just a special case of the dipole antenna. Half wave term means that the length of this dipole antenna is equal to half wavelength at frequency of operation. The dipole antenna is basis for most antenna designs in a basement component with equal but opposite voltages and currents applied at its two terminals through a balanced transmission line. Now, the length is half wavelength, that is lambda by 2, that is a half wavelength. Now, what do you mean by half wavelength? This can be explained clearly by using this example. If an antenna is to radiate at 600 megahertz, this is the frequency at which we want our antenna to radiate. So the size of wavelength will be, we know that wavelength is denoted as lambda is equal to c by f. Now substituting these values, you are getting the wavelength 0.5 meters. The frequency is 600 megahertz and c is the velocity of light. Substituting both the values in the formula, you are getting wavelength as 0.5 meters. Now here we are discussing the half wavelength dipole antennas. So it will be lambda by 2. So lambda by 2, again the value of lambda can be substituted, that is 0.5 meters. So hence the half wavelength dipole antenna length is 0.25 meters. The half wavelength dipole antenna, as you may expect, a simple half wavelength wire fed at the center as shown in this figure. This is the simple half wire, two wire line concept, simple wire that is fed at the center. And considering the example, the length of this wavelength, if it is to work at 600 megahertz, it is 0.25, as we have calculated here. For 600 megahertz operating frequency, this half wave dipole and antenna length will be 0.25 meters. Dipoles have a radiation pattern definite symmetrical about the axis of the dipole, that it is symmetrical at the axis of the dipole. The radiation is maximum at right angles. You are having the maximum radiation at the right angles to the dipole, and they are dropping off to 0 on the antenna's axis. Now again coming to the folded dipole antenna, this